In this little video, I'm going to consider a couple things that may not be that practical, but will give us additional insight into the, the whole idea of how universal gravitation works and some phenomena that you might have thought about from time to time, maybe having to do with our Earth. One being, what would you weigh inside a hollow Earth or a hollow planet? So what I'm showing here is the planet, but it's been gutted, severely gutted, so maybe we only have a few hundred miles thick crust, and the rest of this is just hollowed out. So somehow the thing is structurally able to hold itself up. And there you find yourself all freaked out inside this hollow Earth. You got a atmosphere inside there or a spacesuit on or something. And so the geometry is that you're 2/3 of the way over to one side, so showing these dotted lines, that'll give us some perspective. So your D here, 2D over here. And of course, every piece of mass around here is pulling on you. And we've got a cross section here, which is sufficient to prove the point we're trying to make. So first of all, we have a gravitational tug, and we're considering just from this region. We'll call the mass of that segment M. And then so Fg is G big M little m over D squared. That's how hard that this chunk is pulling on you toward itself. You think of all the stuff over here is pulling back on you. So it's a correct correspondence to think of this piece over here correspondingly pulling you the other way. So that's going to be this F, this unknown F. What is it? Well, F is equal to gravitational tug from this larger piece of mass. Well, what's this? Well, the arc length is double. However, if you think about putting your eyeball over here, this is really a cone-shaped region in 3 dimensions. So this would be a circular piece of mass. And so because we're talking about area, it's a squared quantity. So it's doubled in this dimension, but it's doubled across perpendicular too. Yeah, hopefully that's not too confusing. But if we look at it over here, it's doubling horizontally and vertically. So really we have 4 times the mass here because it's a circular piece. Therefore, the force from this acting on you is 4m times little m times g divided by twice the distance squared. Well, that's 4gmm over 4d squared, or g big M little m over d squared, which is the same thing we had before. Yay! We're all excited about that. So it turns out it was the exact same force. So we're being pulled to the left and to the right with equal amounts of force. Therefore, if the force is 0, the g field, which is Fg over m, is also 0. So I'm not going to try and satisfy any other concerns you have about that. It is actually true, and it's true everywhere inside this region. Even if you're right next to it, if you find yourself right here, you say, this mass is right there ready to just plaster us against it. But if you think about it, almost all of this behind you is conspiring to pull you away from there as well. And the net result is you don't have any net force on you because there's no G field. Therefore, you are weightless everywhere inside a hollow planet. The G field is 0. It's 0 everywhere, which means you are truly weightless and not just apparently, as you are if you're orbiting. If you're orbiting a whole planet or something, then you feel weightless because there's no support force acting on you. Remember, it's your support force that gives you the feeling of weight. So apparently weightless doesn't mean truly weightless. Weight is mass times gravity. You have mass, and if you're out here orbiting, your mass is subjected to gravity. So you have weight, you just don't have any support force. But here, there's no gravity inside, so you're truly weightless. So isn't that a phenomenal little detail? Hope you enjoyed that. And now, because we're having so much fun, I want to consider what you would weigh inside a solid Earth rather than a hollow Earth. Okay, it's a little bit scary being dropped onto the surface of the Earth, but not too bad. There's a person with mass M, If we consider mass over here, here's a force vector corresponding to that mass. Anywhere based on symmetry, you'd have a corresponding mass on the other side. So there's the pull from that. Now I could add little blue vectors here that would just fill the whole screen. But the point is that each one would have a corresponding one on the other side. Okay? And namely, the net effect of all that, when you add all the vectors up, you notice none of them are going, as far as the force on the person, upward. You end up with this as a sum of all the vectors, if you draw them correctly. Fg straight down. So the sum of the forces is the weight. Nothing too profound there. But now let's consider the center. So you're going to go inside the center of the Earth. You're hollowing out the center of the Earth to protect you in a big, thick titanium or tungsten cavity of some sort that's structurally sufficient to hold back the crushing effects of Earth otherwise on you, and it's air conditioned in there and all. So you're sitting there experiencing a good time in the very center of the Earth. Well, if you're there, here you are. You think of different parts of the Earth tugging on you. The mass over here is tugging on you, but you could probably see that based on symmetry, you've got equal quantities of force in every direction, so that the sum of the forces acting on you is actually 0. So you're weightless in there. But really, hollowing out this little cavity is really what we just proved in the previous slide, namely that all the mass in this shell, this is basically just a hollowed out Earth again. It's just it's most of the Earth that's still there, but you're inside this, so all the mass outside of the region you're in doesn't count. It cancels itself out, which is really easily seen here with all these force vectors, moving outward from the center to show that they cancel. All right. Well, now, what's your new weight halfway to the center of the Earth? And by considering that, we'll have answered the question basically. So here's the radius, mass m. Now I'm gonna show a region that's darker. It's still part of the same overall Earth, but it's half the radius. Now don't worry about how the person is standing there encased in the material of the mantle here. That's beside the point. Okay, but what is she experiencing? Well, the new mass, the mass of this inner region, is m prime. It's m prime. And what we recognize is really, here's this mass in question. This, from the point of view where you are, if you're inside it, the material on the shell outside of your region doesn't have any gravitational effect. It's like you're weightless inside a hollow region. I mean, if you took this whole region here out and just had this left, if you're inside, then again, this part doesn't have any effect. So only m prime, this inner region, affects you gravitationally. So what is it? Well, let's answer that question by considering the volume of that region. The volume is 4/3 pi r cubed, so it's proportional to the radius cubed. That's what the volume is, radius cubed. But the volume and mass are proportional. So since mass is directly proportional to volume, considering uniform density here, then that inner mass is only 1/8 the total mass, because basically 1/2 cubed. It's proportional to the radius third, to the radius of the third power. The radius has been cut in half, so that cubed is 1/8. So it may seem like there should be more than 1/8 of the total mass, but it's only 1/8. It's not 1/2, it's not 1/4. Okay, so the new weight at r/2, subjected to 1/8 of mass, but half the radius. Basically, let's compare the forces. The force at r/2 compared to the force at the full radius that we had over here. So it's g m prime m over r/2 squared over gmm over r squared. That's the ratio. Lots divides out here. Big G, little m, r squared, and we end up with m prime over 1/4 all over m. Well, that's a lot nicer. So the ratio then is simply 4m prime over m. But we already know what m prime is. M prime is 1/8 m. So we're going to stick that in for this. And we get 4 times 1/8 m over m, which is 1/2. So we've answered the question, namely that the gravitational force, your weight inside a solid planet, is proportional to the radius. At half the radius, you're half the weight. At 0 radius, you're 0 the weight. You don't have any weight at all. So that's kind of interesting. And finally, how about considering a collapsing star? This time, we're going to let all the mass stay, and we're just going to crush it down. This actually happens out in the celestial realm, where large stars collapse into such enigmatic objects as, well, white dwarfs, neutron stars, black holes. Fg, gmm over r squared. Well, now let's go ahead and collapse this down. The same mass, half the radius. So we got the same mass subjecting us to its gravity, but half the radius. Well, now it's gmm over r over 2 squared, which is 4 gmm over r squared. So what's just happened? Our weight has quadrupled. And really, just because of the direct application of the inverse square law. Let's go down to 1/10. If you're thinking about this, you probably know the answer right away. Same mass, 1/10 the radius. Fg, 100 gmm over r squared. So the conclusion is that Fg is proportional to 1 over r squared, just like we would expect probably. So interesting, coming back here, as we start in the center and move outward, we recognize the gravitational field, or the weight, is increasing linearly with radius. And we get to the very edge, and then poof, immediately it reverts to a inverse r squared relationship. So we go from proportional to inverse square. So that's quite a big difference. And there you are with some additional insight that hopefully put a little cheer into your day.